Hi everyone, my name is Stephen Pu, founder of Taraxa, and today I'm going to talk about how Taraxa uses VRF and VDF as an energy efficient alternative to proof of work. So first let's talk about proof of work, right? So proof of work is a very simple and elegant algorithm that introduces random delay into the blockchain network, right? So why is random delay important? Well, the random part makes it fair, right? No one can predict it, so it's fair who gets to propose the next block because it's random. The delay part is important, as we talked about before. We need to give the network sufficient time for the block to propagate to, a significant number of miners, so that they're actually able to all get the same picture of the network, so that we minimize forking, right? So you need a random delay. But what's very interesting about proof of work is that it's essentially just a guess, right? You're guessing. It's a puzzle that involves you guessing at what a number is supposed to be. And that number, once you calculate it, has some specific properties, and there's no way to really arrive at that answer other than guessing, right? So what happens when you can guess something? Well, if a puzzle is just purely guessing something, then that puzzle can be solved using parallel processing, right? So for example, if I have a puzzle whose answer is basically, it could be 0 to 9, right? That's really the total total of all the possible answers. What I can do is I can just guess 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I can guess it one by one, or I can say, hey, let me get two computers, right? And this computer will guess 0 to 4, and the other computer will guess 5 to 9, right? Then I could guess twice as fast. And probabilistically, on average, I can get four computers, right? And I can get four times as fast, or I can get 10,000 computers, right? And I can get 10,000 as fast. So what that does is that now instead of running just one computer, you're running 10,000 computers, right? And that consumes 10,000 more energy than one single computer. What's even worse than that is that there are mechanisms in place for proof of work chains, such as Bitcoin. Is that when it detects that the interval between blocks has gotten shorter and shorter, which means people are guessing faster and faster with more and better hardware, then it actually raises the difficulty of that puzzle. So now, in addition to having something being parallelizable, you also run into an arms race, right? So now, if I'm guessing 10,000 times as fast, well, the other miners need to make sure that they guess 20,000 times as fast, right? Or else I'm the guy producing all the blocks and earning all the rewards. So you get into an arms race that actually drives the entire network to consume more and more and more energy. So that's why proof of work, while very simple and elegant, is highly energy intensive, right? So what do we do, right? Like we said, if we want to replace proof of work, we need a source of random delay. So let's first talk about delay, right? So the VDF function is called the verifiable delay function. It has this very interesting property in that it is purely sequential, in that you cannot parallel process it, right? Which means that, for example, in order to get to a specific delay, you have to calculate this VDF function many, many, many times, say like 10,000 times or something, right? And but every single time you calculate it, it's not like you can get 10,000 computers to each calculate it one time. It's one computer having to calculate 10,000 times because each subsequent answer depends on the previous answer, right? So basically, the outcome of VDF T is going to be dependent upon VDF T minus 1, right? It's going to be some function involving VDF T minus 1. So that's essentially what it is. So it has to be sequentially done. So it cannot be parallelized. It also has this other property in which that although it must be sequentially calculated, the proof, right? The proof doesn't require the prover to actually do it again, or else that would take an incredible amount of time. So the proof is actually significantly shorter than the actual calculation. Now we got the delay part okay, now we get into the randomness part. So what the randomness part does is that when we talk about randomness, what we're really talking about is fairness, right? So we want to make sure that the outcome of this randomness is unpredictable by any of the players that are involved, right? So so that's exactly what VRF provides, right? So you can think of it as something sort of like you're signing a bunch of things that are available on the network. For example, the block you're pointing to, the level that you're at, the block hash of the last period block, whatever, right? So you can get a whole bunch of sort of, you can get a whole bunch of independently generated sources of information that are not predictable ahead of time, and then maybe just sign it, and then you get a completely unpredictable outcome, and whether that outcome obeys a certain threshold, above or below a certain threshold, is uniform, is very much uniformly distributed. That's the characteristic of VRF, right? So on the Taraxa network, eligibility for a block proposal is determined by several things. One is, of course, staking. That determines whether or not you're actually a block producer at all. Number two, it depends on a randomized delay, a delay that is random, right, with some inputs, right, and then some inputs with a verifiable delay function. So what we're doing here is that we're taking this combination of VRF and VDF to replicate the random delay of proof of work without the energy waste. So that's how we do it. That's how we handle block proposals inside Taraxa. All right, thank you.